So good afternoon, I'm Poli, and today I will talk about my first year of PhD in the EP2 plus, EP2 group with a thesis on advanced 2D fluid modeling of all effect discharges directed by Pablo Fajardo and Eduardo Edo. Well, a small introduction. I mean, you all know now what are all thrusters. Anyway, they are called plasma thrusters since they accelerate the plasma as a whole, and they rely on E cross B field, which confines the electron in azimuthal motion. This creates an electric field, an axial electric field that accelerates the ions to velocities in the order of 20 kilometers per second. On the right, you can see a schematic of a whole thruster, and on top, a nice photo different from the one you've seen before, because this is a two-channel nested Hall thruster for very high power, roughly 50 kilowatts. The motivation behind my thesis are the fact that in spite of Hall thruster being used since many years in space, we still don't know many things. And as you've learned today, one of those things is the anomalous transport. So the enhanced axial mobility of electrons, which cannot be explained through classical collision theory. There are two possible causes, which are near-wall conductivity, developed first by Morozov, or the onset of plasma instabilities, among which we can find on the axial direction ionization instability that some call breathing mode, or ion transit instability, and on the azimuthal direction, rotating spokes, what are called rotating spokes, and electron drift instability. As you've seen, we are mostly interested in the azimuthal one, how they grow, how they dampen, and how they couple, well, maybe also with the axial ones. The state of the art of this model is that there's just a few of two-dimensional axial azimuthal model, and the only models available are either hybrid, which means, well, fluid electrons and particle in cell heavy species, or full particle in cell. In my thesis, I have to develop a fully fluid two-dimensional axial azimuthal model, which will allow for faster simulation with respect to the particle in cell and a direct comparison with particle in cell simulation in order to evaluate whether these instabilities can be described effectively by a fluid approach or they are prevalently of kinetic nature. So the goal of my thesis, and the primary goal, is the one of developing a two-dimensional axial fluid code, axial azimuthal fluid code, and to study and characterize the azimuthal instability. But during the first year, we came up with actually secondary tasks, secondary goals, with, for example, the development of a one-dimensional fluid code to study and address axial instabilities, but also the matching of this one-dimensional code with the hybrid code in-house developed, the hyphen, axial radial, that you've heard before. And the idea is to use my code, which is much, much faster than hyphen. It takes roughly minutes, maybe less, with respect to tens of hours of hyphen simulation, in order to provide the hyphen for anomalous transport profiles, which are, let's say, tailored on experimental measurements, so that in the end, we would have a tool that can help hyphen speed up the process of matching and simulating experimental thrusters. So the methodology that I will be using, and I've been used in this first year, is to increase the complexity of the model I'm doing gradually, starting from a simple model, such as the one-dimensional, and increasing its complexity based on the step before, so that each model actually as a global perspective of the final goal of the thesis, which is the big two-dimensional code. And each model is developed such that it can be easily expanded, physics can be added, multiple dimensions can be added, or more fluids, so that in the end, the process of building the large code, my final goal, is easier. Moreover, there's the study of in-house codes, such as EP2 plus and hyphen, so that I can either reuse or upgrade technical solution methods, or other aspects. For instance, I'm going on a different direction for what have been done for now, which is a shared memory parallel computing towards distributed memory parallel computing, in order to create also a know-how in the group, and this might be useful for the future. Moreover, I can take advantage of existing physical models so that the cross-checking with the well-established code would be much easier, and I'll show an example of this later. So the accomplished tasks that I've done in this first year are the development, first of a non-neutral one-dimensional axial code with full electron inertia that for the moment has been set aside due to the prohibitively small time step required to solve the Poisson equation and to resolve complete electron inertia, which for a one-dimensional model is not in general justified, but we might continue on this road in the future. Then I developed a one-dimensional quasi-neutral axial code where only partially the electron's inertia is retained along the azimuthal direction, with which I studied preliminarily the axial instabilities, ionization instabilities, and something about ion transit instability. Ongoing tasks are the development of the two-dimensional code and the reduction of to, let's say, one dimension of hyphen results in order to obtain phenomenological relations that will enable my model to match hyphen results and then develop this tool to help hyphen with the anomalous transport profile. Going to more technical details, the one-dimensional model, here you can see an overview. On the right, you can see a schematic of the computational domain. It is a one-dimensional time-dependent model with some novelties with respect to the literature that have never been introduced in this kind of codes, such as a volumetric layer cathode here, which allows to extend the diverging plume up to, well, the domain up to the diverging current-free plume, and the introduction of electrons azimuthal inertia, which has important effect close to the anode especially, and some close to the cathode. I also characterize better the heavy species by introducing, well, ion energy equation, but also neutrals momentum and energy equations, accounting for the effects of ion that recombines at the wall and re-enters the domain as neutral, and can depositate some energy in the neutral flow. Here are some results. On the left, you can see the dynamical behavior of a discharge, where you can see clearly the breathing mode, this strong ionization instability, which impacts the plasma density, neutral density, but also all the other quantities, such as the electric field or the electrons temperature. On the right, you can see the stationary behavior of a plasma discharge, and in particular, this is a comparison with the stationary model developed by Enrique Bello, and this is something I was saying before. The cross-check is natural, is easy, because of the similarity between the physics behind the two codes. And as you can see, the two codes, my stationary solution and the stationary model from Enrique matches perfectly. Some interesting results we obtained regarding the neutrals. In particular, we've seen that in introducing energy to the neutrals, accounting for these ions that recombine at the wall, have an impact on the stationary solution, as you can see on the right. Well, input, with higher energy input, we can see higher velocity, higher neutrals temperature, lower temperature of ions in the plume, and so on. But also on the dynamical behavior by promoting the onset of stable breathing mode in the thruster, which is not always resolved by one-dimensional model. And indeed, usually in the community, there is the tendency of discarding the effects of neutrals, since they are considered as a background species with not many, let's say, effects on the dynamical behavior of the thruster. But clearly, it's not true. Another aspect is the introduction of electrons inertia. As you can see, we can see the effects near the anode and near the cathode. In particular, near the anode, it bounds in certain conditions where the ion backflow towards the anode is small, which is a condition while we're going towards a reversed sheath, anode sheath condition, or no sheath. The velocities azimuthal and axial electrons velocities are bounded, and their energy are bounded as well. This means that on the dynamical behavior, the oscillation will be damped faster, and well, actually, this helps also the code not to fail, because one-dimensional code, these codes are not meant to work in a reversed sheath or no sheath condition. So if we mitigate this effect by introducing electron inertia, we make the code more stable, especially when breathing mode occurs. For the scientific production, in this year, I presented my work at the Space Propulsion Conference in Estoril last May, with an oral presentation plus a conference paper, which actually won Best PhD Paper Award. And a work in progress is a journal paper based on the conference paper one. For future works in the next year, I foresee to complete the development and testing of the two-dimensional code and of the tool that will help Python with anomalous transport. And also, I would like to address a deeper characterization of axial instabilities, so ionization and ion transit, including the physics that it is usually disregarded, such as neutrals dynamics and electron azimuthal inertia. And finally, I foresee at least a publication of the aforementioned journal paper and, well, hopefully another one. Thank you for your attention, and if you have any question,